Good morning, day 6. Welcome to the live.
All right, all right. Good morning, good people. What's going on, Brian? Tapasarian,
Good morning.
Elaine, Kevin, Charles, Leah and a half, Leah and a half. Can't believe today
on a rotating drum. Then a laser discharges a lower electrical charge on the drum. So basically the laser draws the image that is going to be printed on the drum itself. Then the drum is coated with a fine black powder known as toner. And as the drum is being coated, the toner only clings to the areas where the laser has drawn. Then as the paper goes through the printer, the toner is placed on the paper. And the result is a high quality print that is second to none. And another type of printer is called a thermal printer. Now thermal printers print by using heat. Thermal printers use special print paper called thermal paper. And on this thermal paper is wax-based ink. And when heat is applied to this ink, it turns black. So in a thermal printer, the only thing the printhead does is apply heat to the areas where ink should be printed. Then when the ink is cooled, it becomes permanent. And because of this technology, thermal printers are very quiet. Thermal printers are commonly used for printing labels and barcodes. And lastly, there's dot matrix printers. Now, dot matrix printers are almost non-existent today. They are an old technology that produced mediocre print quality, especially when compared to laser or inkjet printers. And they are also very noisy. Now, dot matrix printers are impact printers. The printhead in a dot matrix printer moves across the paper, and as it moves, the pins on the printhead strike against a cloth ink ribbon, which then comes in direct contact with the paper, producing each character in the form of dots. But despite being an outdated technology, dot matrix printers can print multi-copy documents such as carbon copies. They are also very durable and they last a long time.
Hi, my name is Aaron Sampson. A deep understanding of network services is crucial for IT professionals responsible for maintaining system connectivity and performance. In this course, we'll explore IP addressing, including the role of IP version 4 and IP version 6, along with the role of subnet masks, the differences between private and public addresses, and automatic private IP addressing, or APIPA, DNS and DHCP services, gaining the skills necessary to configure and troubleshoot name resolution and dynamic IP assignment, examine critical server roles such as file servers, web servers, authentication services, and database management systems, explore the network time protocol, internet appliances, and legacy embedded systems, ensuring a comprehensive grasp of modern network infrastructure, and develop expertise in managing network resources, securing network services, and diagnosing server-related connectivity issues, helping to prepare you for CompTIA A+ certification and IT networking roles. In this video, we'll take a look at some characteristics of IP, or Internet Protocol addressing, particularly with respect to the two versions of IP that are in use. But just quickly before we get to that, any IP address functions as a unique identifier that is assigned to any given device so that it can communicate over a network. Now, this functions similarly to a postal address because it enables data exchange between systems, and this is essential for networking, security, and remote access in virtually any IT environment. In short, if my system wants to send any type of message to your system or vice versa, they each need to know the IP address of the other system. So then, with respect to those versions, there are two that are in use. The first is IP version 4, which uses a 32-bit address space. Now, we'll talk about that in greater detail in just a moment. But this limits the entire address space to approximately 4.3 billion addresses. Now, that might sound like a lot of addresses, particularly for any given network. But if you consider every single device that is on the public internet everywhere in the world, this is nowhere near enough addresses to provide each device with a unique address. So as a result, IP version 6 was introduced, which uses 128 bits for its address space, which vastly expands the available addresses. Now, I'll expand upon that in just a moment as well, but I do want to point out that there seems to be no IP version 5. And this, in fact, is because IP version 6 did begin as version 5, but as they were going through development, the changes were significant enough and the time span was long enough that they really just ended up designating version 5 as a prototype, for lack of a better word, for version 6. So it was more of a research version than version 6 was actually released. So there is no functional version 5. So as to some of the characteristics between the two, coming back to that address length, again, it is expressed in version 4 as a 32-bit address. Now, this means that each component of the address is actually a binary value. So whereas we see its format in what's known as dotted decimal, such as 192.168.1.10, the values themselves are actually binary. It takes 8 binary bits with values of either 1 or 0 to express any one of those dotted decimal values. So 192 takes 8 bits to express, 168 takes 8 bits to express, and every value in the address is made up of a combination of 8 ones and or zeros depending on what the value is. So if you have 4 numbers, again, 192.168.1.10, that's the 4 numbers, and each one takes 8 bits to express, then that's 4 times 8 is 32 bits. Now, the IP version 6 address uses 128 bits, and that is exceptionally larger, because the way that binary works is that if you add even one more bit, the total number of possible addresses doubles. So 32 bits provides for approximately 4 billion addresses because it's 2 to the power of 32. And the reason it's 2 is because a binary value is either 1 or 0. So it can be 2 possible values. So 2 to the power of 32 is approximately 4 billion. 2 to the power of 33 is approximately 8 billion. So you double the address space with just one more bit. 2 to the power of 34 is approximately 16 billion. So by the time you get to 128 bits, this number is astoundingly large. It is quadrillions upon quadrillions upon quadrillions of addresses. So it's also far too long to express in a dotted decimal notation, so the format uses hexadecimal characters. And where the address space of IP version 4 does accommodate for approximately 4.3 billion addresses, in IP version 6, it is virtually unlimited. Now, 2 to the power of 128 is an exceptionally large number, but it is still a finite number. But in practical terms, it really is virtually unlimited because it's so large, it allows for every single person on Earth to have billions of addresses just for themselves. So again, it is in practice unlimited. In terms of security, it's optional in version 4. You can use features such as network address translation and IPsec or IPsec, which is the secured implementation of IP. But in version 6, it's built in. So IPsec is always used in IP version 6. And as far as the configuration of the address is concerned, with IP version 4, we tend to use DHCP most of the time, which means that devices will receive their address configuration automatically from a DHCP server, or you can manually assign the address on any device at any time. Now, IP version 6 actually supports both of those, but its primary configuration method is through auto configuration of the device itself using a process known as SLAC, which stands for Stateless Address Auto Configuration. So devices initialize themselves with their own addresses automatically. And because of the size of the address space, the chances of any two devices initializing with the same address is highly, highly unlikely. But even if it does happen, they'll realize it and one of them will reconfigure. So address conflicts don't happen in IP version 6 unless someone manually assigns the same address twice. And finally, with respect to some other differences between the two, again, the address space for version 4 being the 32-bit address is expressed as that dotted decimal notation. So we see an example here of 192.168.1.1, and those are the 4 octets because, once again, there are 8 bits in each one of those values. Now, even though we don't see them as binary values, that's how the protocol works. We just use those values because they're easier for us to work with. IP version 4 also uses subnet masks to define the network and host portions, and we'll talk about that in greater detail in the next video. But in short, the subnet mask defines the size of the network and on which network any given device resides. But again, due to the growth of the public internet, IP version 4 does not have enough addresses to publicly address every device. So IP version 6, with that 128-bit address space, is written in hexadecimal format. And here we see an example of 2001, then a colon, then DB8. Then if you see 2 colons right next to each other, it means that all the values in between are all zeros. So that would be 0000, FF00, then we only see 42, so that would mean that the ending characters are also zeros, so you can do that as well, then 8329. So again, that's just an example, but as mentioned, it supports that stateless auto configuration, enhanced security because IPsec is used by default, and that much, much larger address space. Now, to finish up, while IP version 6 is much more accommodating for the internet of today, IP version 4 is still very commonly used in internal networks because of its relative simplicity. So I suspect that you'll still continue to see IP version 4 used for quite some time, But as for the public internet, IP version 6 is much more commonly used. And while the two addresses themselves aren't compatible in that if I'm using IP version 4 explicitly, I must communicate with another device using IP version 4, any given device can support both protocols. So you can have both installed, and as long as you have one of them in common, then you'll use that version. So again, I think you'll continue to see IP version 4 used in internal private networks for quite some time, but things will gradually move to IP version 6, by which time there might likely be another version, but for the time being, both can be used in just about any situation. In this video, we'll take a look at some IP address considerations that are specific to IP version 4. And perhaps the most notable characteristic is the use of what's known as public and/or private IP addresses when dealing with version 4. And the reason that these exist is because, quite simply, the address space of IP version 4 is not large enough to accommodate a unique address for every single device on the internet. So public IP addresses are globally unique, and as far as you and I are concerned, they're assigned by our internet service providers, although they get assigned banks of addresses by other organizations that govern the use of IP addresses. Then the ISP can decide how they want to allocate them. But again, you and I would receive a public IP address from our ISP, and this enables communication over the internet. So even for us at home, there is always at least one public IP address, which in almost every case is on the outward-facing interface of our routers. And this connects us to the ISP and therefore the rest of the internet. An example of any given public IP address is Google's DNS server, which uses 8.8.8.8. Private addresses, however, are reserved for internal networks, so we can use them however they like because they cannot be accessed directly over the internet. So they're commonly used in homes, businesses, and enterprise networks. And the reason why I say we can use them however we like is because of these private IP address ranges, known as Class A, Class B, and Class C. Now, these were defined in what's known as an RFC, which stands for Request for Comment, but it's basically just a group effort, for lack of a better word, of various entities that contribute to the development of the protocol. So these classes have their default sizes, which refers to the number of devices that can exist on any given network. And Class A's are quite simply very large. That particular configuration only uses the first value to indicate the network, then the remaining 3 values indicate the host addresses on that network. So in other words, in a Class A network, 10 is the address of the network. Then something like 0.0.0.1 would be the first usable address on that network. So if you only have 1 octet to indicate the network and the remaining 3 to indicate the device on that network, that means that you have 8 bits to identify the network and 24 bits to identify the host on that network. So 2 to the power of 8 is only 256 possible Class A networks. 2 to the power of 24 is approximately 16 million. So there can be that many devices on any given Class A network. So that's a very large network. Class B networks divide right down the middle, if you will. In other words, 172.16 is the network address for Class B. Then something like 0.1 would be the first usable host address. So if it splits right down the middle, that means there are 2 to the power of 16 possible Class B networks and 2 to the power of 16 possible host addresses. And in both cases, that's around 65,000. So Class B networks are significantly smaller than Class A, but still fairly large. 65,000 addresses on any single network is still a lot of devices. So Class C networks are quite small. They're the opposite of Class A's. In this case, 192.168.0, the first 3 values indicate the network. Then the first possible host address is 1. So there are 2 to the power of 24 Class C networks. In other words, a lot of them, but each one is very small, only 2 to the power of 8 devices. So that's only 256 possible addresses on any single Class C. So this is what you very commonly see in home environments and perhaps small offices. But I will quickly tell you that it's not uncommon to see the Class A addresses even in a network that isn't very large, quite simply because the address is very simple. 10.0.0.1, for example, is a very easy value to remember, so it's not all that uncommon to see them in use. But again, coming back to the point that private IP addresses cannot be accessed directly over the internet means that any of us can use any of these private address ranges however we like, because any given private network does not communicate directly with any other private network. You have to go over the public internet to do so. So this means that it doesn't matter if you use the exact same address configuration as I do. In fact, in almost all home environments, it's quite likely that the exact same Class C addresses are being used, but they don't see each other directly, so it doesn't matter if the addresses are identical. They don't cause any conflicts when you're in the private network. So this helps to alleviate the fact that there aren't enough addresses for every single device. But in our private networks, we don't need public addresses. We can all have a private address as long as there is at least one public IP address assigned to our router. We can all go through that router, and everything coming out of our network appears to have originated from that interface. So since it's a public address, we can use the public internet while still using private addresses internally. So again, the reusability of these private addresses helps to alleviate the fact that there aren't enough addresses to publicly address every single device. Now, in terms of the subnet masks and what's known as CIDR notation, which stands for classless interdomain routing, but it's still a subnet mask, so these are used to define the network and host portions of the IP address. So I just mentioned a moment ago that we have Class A, Class B, and Class C, and each one has a division whereby it separates the network portion of the address from the host portion of the address. So as an example, a subnet mask of 255.255.255.0 is the default subnet mask for a Class C network. Recall that I mentioned in a Class C, it uses the first 3 values to indicate the network portion, and only the last value to indicate the host on that network. So what you're seeing here is the fact that when the 255 changes to a 0, in this case for a Class C, it's after the 3rd octet. So the 255s separate or mask those values from the host portion. So they don't really see the network portion in terms of intercommunicating with the other devices on that network. They just see the last portion, for lack of a better word. So if I'm address number 10 on my network, all I need to know is the address value of another system, such as 11, to communicate with it. The network portion of the address would be the same for both of us. In other words, it might be something like 192.168.1. So we're both on the same network because that's the network address that we both have. But I'm number 10 on that network, someone else is number 11. But again, that's just a default configuration. CIDR, or classless interdomain routing, removes this class configuration. So where Class A's, B's, and C's have those specific divisions, they don't have to be that specific. Now, just quickly, the slash notation is just another way to refer to the address configuration, as opposed to saying 255.255.255.0. 255 in binary is all ones. So the subnet mask that we see on the left side of all 255s in binary is 8 ones dot 8 ones .81.8 zeros. So what you'll find is that there are 24 ones in total. That's what the /24 means. But the division between the network and host portions does not always fall in between the dots, if you will. In other words, the /24 in this case for a class C is just a default value, meaning that we aren't subnetting this network environment. We're using it in its default state. But using CIDR, it can enable more efficient use of IP addressing than classful. So again, class A, class B, and class C are just starting points, if you will. So to give you a better idea of what that means, if we look at the example of /24, again, it does mean the same thing as a subnet mask of 255.255.255.0, meaning that 8 bits remain for the host addresses, okay? Now, the number of hosts per subnet in this case means that there are 8 bits remaining. Now, 2 to the power of 8 is 256, but 2 addresses are never used on any network for host addressing. The first address of the network and the last one. Now, it doesn't mean that those addresses are invalid, they just aren't used for standard hosts. The last one, which in this case would actually be 255, is the broadcast address, meaning that this address is used when you want to communicate with every host on the network. The first address on the network is the 0 value, and this is what routers use to simply identify the network. In other words, it means no particular host on the network, just the network itself. So again, the first address, or the 0 address in this case, means no host. The last address, or the 255 address, means every host. So everything in between can be used for your regular devices. So the number of hosts per subnet is always 2 to the power of however many bits you have, in this case 8, which is 256, minus 2, okay? So if we look at /26, this means that there should be 26 ones in the subnet mask. So 255 is 8 ones, 255 is 8 more, 255 is 8 more. Now we're at 24, but instead of 0 in the subnet mask, we now see 192. Again, there are 8 bits in every value. So each one has a value in and of itself. The first bit has a value of 128. The second bit has a value of 64. The third bit has a value of 32. The fourth is 16. The fifth is 8. The sixth is 4. The seventh is 2. And the eighth is 1. So what you do is you enable each bit in sequence in this case, so that we have the 128-bit enabled and the 64-bit enabled. That's 128 plus 64, which is 192. That only leaves us with 6 bits remaining to address our hosts. 2 to the power of 6 is 64, minus 2, which is 62. And if you went all the way to /30, this only leaves us with 2 bits remaining, because there are 32 in total. So in this subnet mask, we see 255.255.255.252, which means 6 bits have been enabled, leaving only the last 2. 2 to the power of 2 is 4, minus 2 leaves us only 2 hosts per subnet. Okay, now that's just an example, but that's the way that subnet masks and the equivalent CIDR notation can be used to reduce the size of a network if you feel like it's simply too large. Now, with respect to the addressing methods, there are 2 options. You can statically assign any given address on any given device, which means you manually sit down and you configure the values. As such, it will remain unchanged until you or someone else changes it. So this is very commonly used for servers, various network devices such as routers and firewalls, and remote access systems. Dynamic addressing means that the addresses for client systems is typically assigned through the dynamic host configuration protocol, which means that there is a device such as a server assigning the addresses to the client systems. And this address can change periodically, and this is very commonly used for home environments and office devices and in most enterprise networks as well, because we don't have to go to every single device and manually configure them. So it saves a significant amount of time and effort. As for comparing the two, static IP addresses, again, must be configured manually. They're commonly used for servers and remote access, and they're very reliable because, again, the address will never change on its own. Dynamic addressing, however, is done via DHCP. It's used on just about every standard device, particularly in home networks and really any network. But it may change periodically, so they're not as reliable, but typically standard devices don't really worry about that. So again, this is why things like servers and remote access systems tend to have manually or statically assigned addresses because they are consistent, they don't change. But our client devices really just don't need that. As long as they have any address, then they can communicate. Now, with respect to automatic addressing, there is another option known as a PIPA, which stands for Automatic Private IP Addressing. And this is a fallback version 4 IP address that will always use something in the 169.254 address range. Now, as the /16 indicates, this uses a 255.255.0.0 subnet mask, which is the default for a Class B. So it accommodates approximately 65,000 addresses. But the idea is that you might not always be able to contact your DHCP server. Standard networking issues might prevent it. So if the DHCP server is unavailable and your device is trying to receive an address automatically, then it will assign itself this private address automatically. And this allows for local network communication, but only amongst devices that have also received an APIPA address. But it does not allow for any internet access. So in fact, a PIPA is actually better used as a diagnostics tool. In other words, if you have a system that can't seem to communicate, check its IP address configuration, and if you see any address that starts with 169.254, then you know that this system was unable to communicate with the DHCP server. So check the server functionality, but of course also ensure that all network cables and or Wi-Fi settings are correct, because it could just be a networking issue and nothing wrong with the DHCP server. So again, while it is meant to maintain functionality, it's more useful as a diagnostics tool. Okay, so again, these are some characteristics that are a little more specific to IP version 4. But since IP version 4 tends to be very commonly used in internal networking environments, you will almost certainly still be working with these types of addresses. In this presentation, we'll provide an overview of the Domain Name System, or DNS, which is a hierarchical naming service that translates human-readable domain names, or friendly names, such as example.com, into an IP address, which of course is required by the TCP/IP protocol. So by allowing us to use names instead of IP addresses, this functions as a directory for the internet, which enables more user-friendly web navigation, because without it, we would have to remember the IP addresses for the websites we want to view. So DNS plays a crucial role in website accessibility, but also for email delivery and the services that are running in your own network, because it also translates the names of your servers and client devices into IP addresses as well. Now, with respect to how it works, basically it begins with a user request. So we open up a browser and we want to go to myfavoritewebsite.com. So that request goes to our recursive resolver, which essentially means the DNS server that's in your network environment or configured by your ISP for home internet. But if you look at your own TCP/IP configuration, there will always be at least one DNS server listed, very likely two. And that's the system that you always contact whenever you need a name resolved. Now, that server, of course, is not able to know every name on the internet, so it often has to go through this cyclical process, if you will, which is why it's known as recursive. So if it's not able to resolve the name on its own, in other words, it does not know the IP address for the website that we just requested, it will contact what's known as a root server, which in terms of name resolution can be thought of as literally where the internet begins, or at least the process of name resolution. Now, root servers are maintained by external entities, but they begin the process of locating the server for us. Now, the root server does not know every single name on the internet either, but it does know about the servers below it in the hierarchical name structure, which are known as TLD servers, which stands for top level domain. Now, we'll see examples of these in just a moment, but these would be the .coms, the .cas, the .us, .gov, .edu. So that's the last portion of any given DNS name, such as myfavoritewebsite.com. Now, it's also the most generalized portion. In other words, there are millions of .com names out there. So we haven't narrowed things down a whole lot, but we are still getting there. So it would know of all registered entries for something like .com. It would then pass us off to what's known as the authoritative name server, which is the entity that registered their particular name. So this would be the myfavoritewebsite.com server. This does have to be publicly registered. So if you want to start a new website yourself or a new business, you must register the name, and you have to basically say that this is the DNS server that is authoritative for this domain. This ensures that no one else can just stand up their own DNS server and say, well, we're the authoritative name server for this domain. They can't do it. It has to be publicly registered. So once you have that, you are the authoritative server for that domain. Then you can decide for yourself which server is going to be your web server or your www server, and the connection is established. So the IP address is passed back through to the recursive resolver, which then says, here you go, client. Here is the IP address for the name that you requested. So again, it has to do a lot of back and forth, if you will, but ultimately you will receive the IP address. And even though I say it has to be a lot of back and forth, this happens in most cases within a matter of milliseconds. So it's nothing that we would really consider to be slow. Now, in terms of some common DNS records, these are what you can configure within your authoritative environment. And perhaps the most common is what's known as the A record, which stands for address. And this simply maps a domain name to an IP version for address. Now, there is an IP version 6 equivalent, but it's known as a 4A record, and it does the exact same thing. So it simply says this domain equals this IP address. So again, this is the most common type of record. So if I am configuring something like a web server, then the name I'm going to give that server is, in many cases, something like, that's literally the internet name of that server. Then the domain name portion is something like myfavoritewebsite.com. So the A record simply says that equals this IP address, and that's what we receive as a response when we issue that initial request. A CNAME record stands for canonical name, and it's known as an alias, which can equate one domain name to another, or one server name to
All right,
another.
everybody, I was handling a phone call. I know for those that are having issues with getting into
email server,
Measure Up.
mail.mydomain.com.
So,
But for people who are
Aaliyah,
using
yours
the
is not
browser
letting
accessing
you
the
into
mail
your
over
account.
the internet, you might call that same
I didn't
server
log in.
web tests or to deliver them if everything seems to be legitimate. As for the DNS hierarchical structure, this is what I was referring to earlier when a server does all of that back and forth requesting of information from various servers. So as mentioned, it begins at the root, which is the highest level, and this is quite literally represented by a period or a dot. And in fact, many people will call the servers the dot servers. But while we never see this in the address of a browser, the actual or official DNS name, if you will, of any given entry is something like company.com dot. So the dot refers to the root level, and the dot not only represents the root, but it's also the least specific portion of the name. In other words, as you move to the left of the name, things get more specific. So at the top level domain, we see .com, .org, .net. Again, officially it would be .com, . We just don't see the dot. But at least now we're a little more specific. If I know the name ends with .com, then I can forget about all the others. So I've narrowed down my search a little bit. From that point, we go to the second level domains, which are publicly registered. So again, if I want to start a company tomorrow and build a website, I have to publicly register something like mycompanyname.com. Okay, now we're even more specific. I own this domain, so it is registered to me. Then, if you want to, you can also create subdomains, which are extensions of the primary domains. For example, if I have a very large organization, I might divide it up geographically. So I might see east.company.com or west.company.com or anything else. It doesn't matter how you divide it up or what you call it. It's just typically done because it's a large environment. You might want to do it for security reasons, to keep one domain separate from another. Again, that's entirely your call, but this is how servers traverse through that structure to ultimately find the server, because once you get into the second level domain, it's up to that organization to ensure that they create all of the necessary DNS records that we just saw so that people can find the web server and the mail server and any other server they're looking for. So as for those records, they're all stored in what are referred to as DNS zones. So again, this is me within my organization creating all of the records for my systems. So I enter all of that information into a primary or a master zone, which holds the authoritative records for the domain. But that would only be a single instance of that zone on a single server, which by definition gives me a single point of failure, which I don't want. So I can create secondary zones, which are read-only copies of the primary zone for redundancy. So if the primary fails, I have at least one secondary, and you can have as many as you like, which can still handle requests for name resolution, but do take note it's a read-only copy. In other words, you cannot make changes to the secondary zone. The change must be made in the primary zone, which is then replicated to all secondary zones. Optionally, you can also create what's known as a stub zone, which contains only the essential records to reduce query times. Now, the essential records are up to you, but they typically include all DNS servers that you have and perhaps your mail servers and web servers, but again, that's up to you. As far as DNS configuration best practices are concerned, for any given client system, you can actually use publicly available DNS servers. For example, Google offers a DNS server with the address of 8.8.8.8, and Cloudflare is 1.1.1.1. So if you're on something like a public Wi-Fi network, you don't really know who the internet service provider is in that case, so you can actually configure your own DNS servers and use these values. Even within a corporate environment, for your own DNS servers, if I'm the DNS administrator, I can actually enter in one of those values as a secondary server. So my own server would still be responsible for going out onto the internet to resolve names, but I can use one of these as a backup. So if for any reason I can't seem to resolve an address, I can use one of these values as a secondary system and it will query those. You can also implement what's known as forward and reverse lookup zones for more efficient name resolution. A forward is the default or the normal type of name resolution wherein a client knows the name, but they need the IP address. So a reverse lookup zone is the complete opposite. They know the IP address and they're looking for the name. There are some cases where reverse lookups are used for verification purposes. You can also implement DNS security extensions or DNSSEC to prevent spoofing attacks. DNS is a very common target because if an intruder can ascertain all of the names and all of the IP addresses of your systems, then their attacks are much easier to focus, and they can also change records so that users are redirected off to different servers, which would enable them to send legitimate requests off to a malicious server instead. And you can also optimize TTL or time to live values to balance speed and accuracy. And this simply comes down to the fact that names can change, so can IP addresses. So the TTL value determines how long that resolution will remain in the cache of a system that just resolved it. So if it's in the cache, when I request a name, it can immediately be retrieved from the cache and the server does not have to go through that whole recursive process. So I get my response very quickly. So that optimizes speed and performance. But if it's in the cache too long, then one of the values might change and it's no longer valid anymore. If it's not in the cache long enough, then it would just expire out too quickly and that whole recursive process would have to happen over and over again. So it can take a little bit of trial and error, but you do want to try to find that balance between speed and accuracy. Finally, as for troubleshooting DNS records, if it seems to be taking too long to resolve a name, then try lowering the TTL setting or try switching to a faster DNS provider, such as the aforementioned Google server. If the DNS server is not responding, simply verify network connectivity, perhaps restart the DNS services on the server. If the DNS records are incorrect, really just double check the DNS configuration settings to make sure that they are correct, because again, names can change, IP addresses can also change. And finally, if it's a propagation delay, DNS essentially does take time to update, particularly with publicly registered records that may need to propagate globally. But you can use tools such as NSLOOKUP or DIG to verify if the name is appearing. Now, in terms of that global update process, it actually does happen fairly quickly, usually within 24 to 48 hours, but it depends on where you are versus where the name server is. So if you're halfway around the world, it certainly could take a little more time. If you're very close, it might only take a matter of hours. Okay? So ultimately, DNS is a required service, and it's certainly something that you'll want to ensure is running reliably within your environment. And then as for clients, as mentioned, you just want to make sure that you have at least 2 DNS servers configured within your local IP address configuration to ensure reliable and fault-tolerant name resolution. In this presentation, we'll provide an overview of the Dynamic Host Configuration Protocol, or DHCP, which is a network protocol that automatically assigns IP addresses to the devices on a network, which in turn eliminates the need for manual IP configuration on each device. Now, this is very commonly used in homes, businesses, and enterprise networks, and it allows you to manage the IP address allocation from a centralized location. In other words, I can sit down at a single server, for example, and determine which addresses are going to be handed out to the client devices. Now, as far as the process itself is concerned, as mentioned, it is automatic, but it does involve some back and forth, if you will, between the client and the system running DHCP. So the client devices, such as a desktop computer or a laptop or any mobile device on the network, is first configured on the local device itself to obtain an IP address automatically. Now, that is the default configuration on most devices, but you can configure a device to have its IP address configured manually, but that would be something that you would have to explicitly set yourself. So again, by default, most devices are set to request an IP address when they boot up. So what will happen is that the client will issue what's known as a DHCP discover request, whereby it broadcasts for an IP address. And it's important to note the term broadcast here, because the device does not yet have an IP address. The only way it can communicate is to send out the request to every system on the network. So it's unfortunately a little bit of a noisy process, but it has to be this way. Until an IP address is assigned, all communication has to be done using broadcasts. So the server will hear the broadcast and it will respond with what's known as a DHCP offer, which basically says here's an available IP address that can be used. Now, there might be more than one DHCP server on the network, in which case the client might receive more than one offer. So the DHCP request is the client choosing any offer and basically saying, I would like to use this address. Now, most environments tend to only have one DHCP server, but larger networks that require redundancy might often have more than one. But even if there is only one, this still happens in that the client says, okay, that address looks good, I'd like to use it. Then a DHCP acknowledgement will come back from the server, at which point the client can bind that address to its adapter and record the lease. Now the process completes and the client has that address, so it can stop broadcasting and start using directed or unicast transmissions. So once you have the IP address, another component is what's known as the lease. And the lease is a specified duration that determines how long the device is able to retain that IP address before it must be renewed. So in short, it's a temporary allocation of the address to that device. Now, you can determine whatever lease you want, but it generally comes down to the environment in terms of how many addresses you're handing out versus how many devices you actually have. In other words, there can be situations where you actually have more devices than addresses, in which case it might seem like you don't have enough addresses. But if it's a situation where not every device is present at the same time, such as if you have mobile devices coming and going, then this might not be a problem. So in those cases, the lease duration tends to be shorter so that addresses are released more quickly. But if you have more addresses than devices, then lease times can generally be a little bit longer. By default, in most cases, the lease duration is around a week. But again, you can set it to whatever value you like. So as far as that renewal process is concerned, for whatever the lease duration is, client devices will still actually go through a renewal process before the lease expires. So what you'll typically find is that there are essentially these time intervals whereby the client will periodically check with the DHCP server. So the first interval occurs at 50% of the lease duration. So let's just go with something like 10 days as the lease duration for easy math. So at 50%, or after 5 days, the client will contact the DHCP server again to just check to see if it can continue to use the address that it was already assigned. And assuming the DHCP server is available, it will typically say, yes, everything looks fine, and it will then renew the lease time back to 100%. So it will go back to 10 days, and the same thing will happen again when it reaches that 50% mark. Now, if the DHCP server could not be contacted for any reason, then it will try again. So a second interval will occur at 87.5%. So somewhere on the 8th day, it will try again. And then the same thing happens. If the DHCP server was available and it responded, then it will once again renew the lease back to its 100% point. But if the client was unable to contact the DHCP server right through to the end date of the lease, then the IP address is released by the client and it must then request a new address. Now, why might the client be unable to contact the DHCP server? Well, if it's something like a laptop and the user takes it with them on something like a business trip and they're gone for the entire duration of the lease, then clearly they will not be able to contact the DHCP server on the assumption that they don't have something like a VPN. But as long as they are able to contact the DHCP server, then the renewals will continue to happen. In other words, let's just assume that a client can always contact the DHCP server. In that case, that client will never release its IP address. Okay, so again, it depends on the situation, but this ensures that systems do have the same addresses most of the time. As for some of the DHCP configuration options, there is an IP address pool that is configured on the server by your administrators, which essentially says these are the ranges of addresses that can be handed out by the DHCP server. So every client will get an address from that pool, but they will also get the subnet mask as determined by the administrators, the default gateway that they should use, any DNS servers that should be used, and as mentioned, the lease duration or that validity period. As for the DHCP server types, there are a few different options. Many of our home routers have DHCP built into them, so these are often used in small office or home office environments, which are typically referred to as SOHO. So if you're at home right now watching this video, then almost certainly it was your router that assigned you your IP address, and these are almost always pre-configured by the internet service providers, but you can change the configuration if you want to. Dedicated DHCP servers are typically used in enterprise networks for greater scalability, meaning that they can simply handle many more clients than something like a SOHO network. You can see thousands upon thousands of systems in some enterprise networks, so dedicated DHCP servers tend to be used in those cases. But coming back to the point about how all of the communications in DHCP initially use broadcasts, broadcasts have an inherent problem in that they cannot cross routers. So a DHCP relay agent is a system on the network that is configured to hear the broadcast requests of certain clients, then to forward those requests directly across the router to a different subnet. In other words, the DHCP server is not in the same network as the client. Therefore, a single system, or perhaps more than one, but let's just go with a single system, it is configured as a relay agent and it explicitly has the IP address of the DHCP server configured within it, so it does not have to broadcast, but it hears all the broadcasts of the clients. It then forwards them directly across the router to the DHCP server, which responds with an address configuration to the relay agent, which then subsequently forwards that configuration to the requesting system. Then there are also cloud-based DHCP services whereby it is simply managed by a cloud service such as Azure DHCP, but of course this is only available when you are using cloud services. And finally, in terms of troubleshooting some DHCP issues, there can still be IP address conflicts, so simply ensure that the pools themselves have been configured correctly. And you can also create what is known as a reservation in DHCP, which ensures that a particular system always receives the same IP address, and you enter in its MAC address to ensure that it always gets this address. But it's still possible for anyone on the network to manually configure any system, in which case they might simply enter an address that is already being used by a DHCP client. So it's certainly not guaranteed that address conflicts will not happen. So just verify the configuration of the pools, any reservations, and any manually assigned systems. If no DHCP lease is received, verify the DHCP server is running and reachable. It may have gone down, in which case no one will be able to contact it. If the assignment seems to be slow, check for network congestion or misconfigured lease times. And if clients are not receiving an IP address, ensure the DHCP scope is properly defined and activated. You can create a scope on most DHCP servers and leave it deactivated while you're troubleshooting or just reconfiguring the server. And if you forget to activate the scope, it will not hand out any addresses. Okay, so ultimately DHCP is a very commonly used service in almost every networking environment. And again, its core feature is to automatically assign IP address configurations so that we don't have to do so manually. In this video, we'll provide an overview of file servers, which are centralized systems that provide shared access to the files in the environment over the network. They're almost always used in business, education, and enterprise environments to store and manage the files that are needed by the users, and they support collaboration, security, and data management by controlling the access to the files. In other words, it's not just wide open. Not just any user can access any file at any time. You can use authentication and permission to ensure that only the appropriate entities can access only the appropriate files. Now, there are a few different options with respect to the types of file servers, including a dedicated file server, which means that the server essentially runs only that role. Now, as far as roles are concerned, these are the services that the server can provide to the clients. So earlier in this course, we talked about services such as DHCP and
Okay,
DNS.
Kevin, I dropped
Those
a
would
note
also be roles.
somewhere else, so hopefully somebody
file
will reach out to you
servers
about mastery
essentially
course
have to have
soon.
this role added to them so that they have the necessary mechanisms in place to support the ability to store and share files.
Mastery is on
So if you
Wednesdays.
have
That's
a
why I
very
want to make
large
sure
and a
if
very
you need to
busy
get in,
environment, then
you
it
handle
would
that.
be quite common
Brian,
to
you
see
good? You're in mastery?
dedicated file servers. But if the
Everybody
environment
should
isn't
check their
all
Canvas
that large
dashboard.
and isn't all that dynamic, then it's
All
quite
right.
possible that the file
Michael's
server
in. Okay,
could
cool.
perform
Leah's in.
other roles as
Yeah,
well.
me too.
Right.
So it can simply handle more
Who's
than
not in?
just managing
Oh,
the
Brian?
files. Now, what the other
Okay,
roles
so
might
you have
be
to send an
is
email
entirely up to you, but a hybrid
to
server simply means that it is performing
add it on
more
the
than
slot.
one
Right.
role. And
All right.
there are
Hold
also
on a second.
cloud-based file servers if you're using cloud services, but it performs the exact same task. It's just located in the cloud as opposed
So it would
to
be
in
the
an on-premises
NC12W,
some of
the
the key features of
CWP
file
hub,
servers
and then a
include
mastery
user authentication and access control.
for the dashboard.
Again, it's not just a matter of
Yep, do you see
every
it?
file being wide open to every user. Users must
No, sir.
authenticate their identities
Oh,
before
okay.
they can access
So,
any of the files
on the
on
slide
that
here,
server.
it
Then, with
says
respect
right here,
to
send an
which
email to
users can
upskill
do
support
what
at
in terms of accessing
mycomputercareer.com.
various files, we configure file
In any
sharing
communication,
and
you have to
permissions so
list
that perhaps people in this
in the
department
subject
are able to
bar
access files at a the ability to centralize your storage and organize everything, typically in hierarchical arrangements such as folders and files. It offers improved collaboration because multiple users can all access the same files. So when you have teams of users all working on the same files, they can all access them. It offers security and compliance because, as mentioned, you do require authentication and you can set file permissions. So if you do need to remain in accordance with any kind of compliance regulation, you can do so. And it's very cost effective because you have that centralized location for storage as opposed to having files all over the place, if you will, which drives up the management effort required. So it just simplifies everything and reduces the management overhead to have a file server. Lastly, some troubleshooting of file server issues might include slow access, so try to optimize the network bandwidth, possibly upgrade the server hardware, such as the aforementioned faster storage subsystems. Permissions errors almost always do not indicate any kind of physical problem, rather just an issue with the permissions themselves. So just check what the settings are, any authentication settings included, as well as any access policies that have been defined in terms of who is able to access what. But if you receive an error that says access denied, that's not a networking problem, it's not a physical hardware problem, that is always a problem with permissions. File corruption or loss can certainly happen, so try to implement regular backups and use RAID or redundant array of independent disks storage solutions. We'll talk about RAID later on in this course, but it essentially uses multiple disks to store the data. So if any given disk fails, it does not result in the loss of all of the data. And in terms of connectivity, just ensure proper configuration of the network settings and perhaps any firewall rules. For example, ensure that the SMB protocol is not being blocked. But ultimately, for any environment that needs centralized storage of their data and files, you should certainly consider the implementation of a file server. In this video, we'll take a look at various different types of servers that you'll find in almost any business environment, and in some cases even in small offices or home office environments. But they include print servers, mail servers, syslog servers, and web servers, all of which provide essential network services to users and organizations. And the idea is that each server type has a specific function, such as document printing, email management, logging events, or hosting websites. So, as mentioned, you're going to find these used in almost any enterprise IT environment, but even small businesses and cloud computing environments need to support these operations. So, you can find them just about anywhere. Now, one other quick point is that these are also often referred to as the roles that can be installed on any given server, which simply enables them to perform these tasks. So, it depends on the environment and the operating systems that are being used. But just as a basic example, for something like a Windows server, these functions are not available by default. When you just install the Windows Server operating system itself, it really doesn't have any particular type because no roles have been installed. So you decide for yourself which roles to install, but they include these roles such as printing services, the mail software, syslog, and or the web server component. But that said, not every one of these types is available as a role. For example, print services is absolutely just a role that you can install. But for an email server in a Windows environment, that requires its own dedicated software. It's not just a role that you can install. But again, it depends on the type of server and exactly what it is that you want to install. So taking a look at each one, print servers are quite simply used to manage and control network printers. It handles all print job spooling, queuing, and job prioritization if you've configured that, but it reduces the burden on user devices by centralizing print management. In other words, we do not need to have a printer at every user station. So let's just go with a fairly small environment as an example of maybe 30 to 50 users. So rather than buying 30 to 50 50 printers, one for each user, you might have just a single server, but you can install a single printer on that server, then everyone can print to that. So again, it centralizes the print management. This is much more efficient in terms of print job management. It reduces conflicts and manages multiple requests. Again, anyone with permission can print to that printer, and it offers remote printing because as a user, my local computer is not directly attached to the printer. It's attached to the network, but so is the server. So I simply print through the server, if you will, to its printer. And this can significantly reduce costs because, again, it minimizes printer redundancy and improves resource allocation because I only need one printer, in this example, on the server, not multiple printers all over the place. As for mail servers, the job is quite simply to send, receive, and store email messages. It does so using a variety of protocols, including SMTP, which is the Simple Mail Transfer Protocol, Post Office Protocol, version 3, and IMAP, or Internet Message Access Protocol, to manage communication. And these are basically required for just about any business, internet service provider, or email service provider. And they also support the addition of email filtering software, but many may have it built in, but this provides security by protecting against spam messages and phishing attacks so that many of those junk emails are not delivered to the users. And they support storage and archiving so that we can retain emails for compliance and backup purposes. And they all offer user authentication, which ensures that I can access my mail securely, but I can't access yours, and vice versa. Now again, this is a component that almost always needs to be installed separately. Most servers will not have a mail component available by default, but something like print services would be available by default on just about any server. Syslog servers are used to collect and store messages from the various network devices and applications that you might have. So it can be used for more centralized security monitoring, troubleshooting, and compliance auditing. And Syslog implements logging standards for event messages so that they typically follow a standardized format, such as having a severity level. They might be just informational messages, they might be warning messages, or they might be critical. That's just one example of how they're standardized. And in terms of network devices, they can also store messages from things such as routers, firewalls, and switches so that we can see what's happening in terms of network traffic. And security event monitoring is provided through Syslog because it identifies potential threats and anomalies, and it supports troubleshooting more effectively as well because it helps your IT teams diagnose network issues because, again, everything is logged. So we just go through the logs to see what's been happening, and hopefully that can help us to narrow down the cause of any given problem. Web servers are the systems that host and deliver web pages to users over the internet, and they use protocols such as HTTP, or Hypertext Transfer Protocol, or HTTPS, which is just a secure implementation to serve content securely. So for example, anytime you're doing something like online banking or just making purchases, that would always be a secure implementation. Examples of web server software include Apache, Nginx, and Microsoft IIS, which is Internet Information Services, and they all handle HTTP requests. They process the user requests, which is to quite simply request the content of a website, then the web server delivers that content. And they also support dynamic content. In other words, they don't just deliver documents and images, they can run scripts for interactive websites using languages such as PHP, Python, and Node.js. And they can also be implemented in a load balanced configuration, which also makes them more scalable. Now, this simply means that there are multiple servers that can all deliver the same content. So instead of just a single server, which if it were to fail, then all of its sites would go down, we have several servers, and they all share the same content, and it's synchronized among all of them so that any given server can respond. So you place a load balancer in front of those servers, for lack of a better word. Then when a request comes in, the load balancer can say, this request will go to server 1, this request will go to server 2, this one to server 3, and this ensures better availability and performance because no single server will become overwhelmed. And if one does fail, there are others available to pick up the load, so to speak. So you very commonly will find web servers in a load balanced configuration. Finally, with respect to troubleshooting various server issues, if it's a print server, then a common issue is finding a print job that's stuck in the queue. In other words, it just won't print, and any other jobs that are behind it in the queue will not print either. So you can typically correct this by restarting the print spooler service or just clearing all pending jobs. If it's an email delivery failure, check the configuration of the SMTP protocol and any spam filters. Maybe the message is being identified as spam when it's legitimate. And if it's an issue of the syslog server not receiving any logs, verify the network connectivity between the device and the syslog server and the logging permissions. In other words, is it able to write to the server? And if the web server appears to be down, certainly inspect the firewall rules because they may be blocking certain protocols and or ports. Check the server logs to see what kind of activity has been happening, and certainly the hardware health, particularly the storage, because web servers rely on the documents that have been configured to support the sites. If they cannot be accessed from the drive, then clearly the site will not be available. So again, there are a number of different types of servers, and which ones you implement are entirely up to you, but these are certainly very common examples for just about every environment. So it's certainly good to familiarize yourself with the common types of roles that are implemented in most network environments. In this video, we'll take a look at servers running the system logging protocol, or more simply referred to as syslog servers. And syslog in and of itself is a standardized protocol for logging system messages and events. And these are used by network devices, servers, and applications to send logs to a centralized syslog server, which in itself is essential for monitoring, troubleshooting, and security auditing in IT environments. Now, just to give you a quick example of logging in general, if you are working on a Windows system right now, then you can click on your Start button and just start typing in Event Viewer and pull that up, and you will see an example of logging. You'll see various types or categories of logs, such as system, applications, security, and several others. And if you select any one of those categories, you'll see all of the actual event messages or log entries in the window in the center. So that's what logging is all about. It just records what has been happening on that system. But in very large environments with hundreds or thousands of servers and devices that all maintain logs, it's very inefficient to go and check the logs on each device individually. So again, the syslog server is a single centralized server that receives log entries from all of these devices, so I do not have to go to each device. I can see the log entries from everything in one place. Now, if necessary, you can certainly set up more than one syslog server, but that's up to you. So the general process then is that the devices themselves generate the log messages based on what is happening on those devices. They are then configured to send those messages to the syslog server. It will process each of those messages and categorize them depending on your configuration, at which point you can then monitor what has been happening, but you can also set up alerts so that if this particular message comes in with these characteristics, you can be informed about it so that you don't have to go manually searching through the logs all the time. It will literally tell you this just happened, and you can then respond. As for some of the key components of a syslog message, they include, perhaps most notably, the priority value, or PRI, which indicates the severity of the log message. In short, some messages are more severe than others, but we'll take a look at the severity levels in just a moment. Then there is a timestamp, which specifies when the event occurred. Then the host name or the IP address, which identifies the source device or where the message came from, and then the message content, which contains the actual log information describing the event that took place. Now, coming back to those severity levels, there are 8 in total, but they begin at 0, and this is effectively the most severe. So we see this is set to emergency, and in essence, the system is unusable in that state. So significant hardware failures, for example, or anything that just renders the system unable to respond. An alert then is immediate action needed, but the system itself might still be running and able to respond to other types of requests. Critical is a severe condition, which would probably still require immediate action, but there might still be aspects of the requested service that are still functioning. An error at level 3 is just some kind of an error in operation, so it typically is not critical, but something failed. Maybe it was disrupted by some other operation, but it still did not complete. A warning is a potential issue, so this is certainly less severe, something that you should pay attention to, but might not require any action, again, depending on what the issue was. A notice is typically normal, but still something that can be significant, so still something that is noteworthy, for lack of a better word. Then informational almost never indicates any kind of a problem. It's just a general operational message, but it does act as a confirmation that something did do what it was supposed to do. For example, if an update was installed correctly, that would generate an informational message to tell you that it did install. Now, debug is the lowest level, but these are typically only used for troubleshooting by developers, so they typically don't mean all that much to day-to-day users. But every syslog message will indicate some kind of a severity level, which helps to determine how you should respond. Now, there are a few different deployment options in terms of your syslog servers, and the first is to simply have them in your on-premises environment. This is certainly good for local security and better access to the server itself and perhaps more direct control over its configuration. But you can also implement cloud-based syslog services, which are highly scalable logging solutions, such as Amazon Web Services CloudWatch and LogLink. But in short, these can just keep growing and growing. So if your environment is quite dynamic and it is getting very large, then you might want to consider a cloud-based solution. And a hybrid implementation simply combines both of those, so you can have a local syslog server and then perhaps one in the cloud for redundancy and or better efficiency. That is certainly up to you and perhaps more so the circumstances of your organization, but any option is available. Now, with respect to some best practices for syslog deployments, if you are going with an on-premises syslog server, then again, the idea is that this can be better managed because it is right there in your own environment, and you might have more control over its security configuration. And this is something that's important to note, although I'll come back to this point in just a moment. But all of the devices in any given environment can generate a lot of logging activity. So you can also set up log rotation and retention policies for greater efficiency in terms of storage. Rotation refers to the fact that you will keep a certain number of days worth of logs, let's just say 30 days for example, then those are archived. We can keep them, but we probably don't need to access them very often. So we have these 30-day rotation periods. And again, this helps to keep things more efficient because the servers don't have to store any more than that period's worth of logs. But coming back to the security aspect, you definitely should ensure that the logs are encrypted and that access controls are in place to ensure that only authorized personnel are able to access the syslog servers and the stored logs, because they contain all of the information necessary for intruders to gain access to your systems. They would include all the names and the IP addresses, and in some cases, even the credentials that were used to log into them. Now, that would depend, but this is the kind of information that intruders would definitely like to get their hands on. So you'll want to ensure that security is in place for your syslog servers, which is one of the options why you might choose for a local server, just for better control over that security. That's not to suggest that they aren't secure in the cloud. They absolutely are. It's just that you might have more control in terms of the security configuration if your servers are local. As for the benefits of using a syslog server, you get this centralized log management. Again, it aggregates all of the logs from multiple devices for much easier analysis, so that, again, I don't have to go from system to system to system to examine the logs. It allows for better security monitoring because it detects any unauthorized access attempts and other network anomalies. These are certainly things that you would find in something like the security log. It can help you to maintain compliance and auditing as well if your organization is overseen by various regulations, including GDPR and HIPAA. GDPR is the General Data Protection Regulation, and HIPAA is the Health Insurance Portability and Accountability Act. And in terms of troubleshooting and diagnostics, basically the logs are just about the first place you would want to start when there is an issue, because it will tell you these are the things that were happening, and or this is what actually happened to cause a particular problem. Finally, if you're troubleshooting issues with syslog itself, they might include the syslog server not receiving logs from the other devices in the environment. So verify any firewall rules and check to see if the service is running on all systems and devices. If you have a very high log volume, in other words, you're being overloaded, implement filtering. For example, you might only choose to save messages with a severity level of, let's say, warning or higher, and consider reconfiguring your log rotation so that it's a shorter period, which in turn would result in storing fewer active logs. If you're receiving any unformatted log messages, ensure proper parsing settings in the syslog software. Now, that would be something that you would have to configure directly on the server, but if you're basically getting unreadable messages, that would be a formatting issue. And if it's delayed log delivery, consider using TCP instead of UDP. Now, that said, TCP is slower, which might seem to increase the delay, but TCP is more reliable. So if it's UDP, messages might simply not be reaching the destination at all because UDP is not guaranteed. So that would also be something that would be configured on the syslog server. Where there is a lot of activity and a lot of logging, you should certainly consider. In this video, we'll take a look at web servers, which in short are the systems that deliver web pages to clients over the HTTP and HTTPS protocols. In both cases, that's Hypertext Transfer Protocol. The S means it's the secured version, and as you might imagine, they're used for hosting websites, but also web-based applications and APIs, or application programming interfaces, which allow access to other applications. And some examples of the software platforms include Apache, Nginx, and Microsoft IIS, but we'll take a closer look at those in just a moment. But as far as how web servers work, the client begins by making a request in a browser for a URL or a uniform resource locator, which then invokes a DNS name resolution, whereby, of course, we need the IP address in terms of communications, but it would have been the name that we would have known. So again, this is where DNS comes into play to resolve that name to the IP address. Once that has been resolved, the connection is established and the browser connects to the web server via either HTTP or HTTPS, depending on the requirements of the page. The server will process that request and retrieve or generate the requested web page or pages, which are then delivered back to the client, and we see them in our browsers. As for the types of web servers, coming back to some of the aforementioned platforms, they include Apache, which is an HTTP open source server that is very widely used, so it's available to anyone. Nginx is a higher performance web server that can also act as a load balancer and a reverse proxy. Now, just quickly, a proxy server is a system that you might have in an internal network environment, so that rather than each individual user having direct access to the internet, everyone goes through the proxy server. So the request is made to the proxy, then the proxy stops the client communication and says, basically, I'll go get that site for you. Then it returns the site back to the client. And this can be used to filter and or restrict sites so that users can only access approved websites, for example. So a reverse proxy is in the opposite direction. Requests are coming into the environment, but the reverse proxy stops those requests and directs them to the appropriate server to handle the request. So again, Nginx can perform all of those roles. Microsoft's IIS, or Internet Information Services, is a proprietary platform of Microsoft, so it runs on Windows-based servers. And Lightspeed is another open source platform that is a performance-focused alternative to Apache. Now, with respect to the web server components, they include the web engine, which processes the HTTP requests and serves up the content. Then static and dynamic content is handled through dynamic HTML files and dynamic scripting languages, including PHP, Python, and Node.js. Logging and monitoring is responsible for tracking requests, logging errors, and displaying performance metrics. And the security mechanisms include implementing HTTPS, firewalls, and various access controls through permissions. And in terms of the benefits of using a web server, they include very high availability and scalability, because you can just keep adding more servers. So if, for example, you only have a single web server and anything happens with that server, then of course every site and or application on that server also goes down. But you can have multiple servers in a cluster, so that if any one server fails, there are others available to continue servicing requests. Or you can create a load balanced array, whereby you still have multiple servers, but the load balancer will balance the requests that are coming in across each instance. So if, for example, you have 4 web servers, then the load balancer would send approximately 25% of the incoming requests to each server. And again, if one fails, it's no problem, the others are still available. The load balancer will just dynamically adjust and send approximately 33% of all requests to each node until the other one is restored. And of course, they also provide security and encryption for things like secure web transactions, and they do so using either SSL, Secure Sockets Layer, or TLS, which is Transport Layer Security, and this includes encrypting the data that is transmitted back and forth. And they are entirely customizable and configurable in terms of performance optimization, and they run on multiple different platforms, including Windows, Linux, and Mac OS. So just about any environment can have just about any type of server. And finally, as for troubleshooting web server issues, if the server is not responding, certainly check the firewall settings and or the server logs, because the firewall might be blocking legitimate requests, and the log should indicate what's actually been happening with those requests. If the pages seem to be taking too long to load, then you might configure some of the cache settings and or enable compression of the data pages so that less information has to be transmitted across the network. As for any security vulnerabilities that may arise, just be sure to stay on top of updates and patches and apply them as soon as they're available. And if you have any issues with SSL certificate errors, just ensure proper installation, and perhaps most notably, the validity period of the certificate, because certificates do have an expiry date. So if it expires, then it will not accept any secure connections. So ultimately, if you do need a web page of any description, it will have to be hosted on a web server. Now, one quick point, these days it's certainly becoming more and more common to just use cloud-based servers, and that's perfectly fine, but you do still have to choose the type of platform that you want to use to host your sites, and you still have to make sure that the DNS registration is implemented. But in many cases, the cloud provider might be able to handle that for you as well. But again, that's entirely up to you. If you have a web server within your on-premises environment, then all of the same considerations apply. It really just comes down to where do you want to host your websites. But one way or another, you'll need some kind of a web server in order to do so. In this presentation, we'll examine authentication, authorization, and accounting, or AAA as it is sometimes known, which in the context of information technology is a framework for managing network security. Now, in one form or another, it's almost universally implemented in enterprise, cloud, and service provider environments to control access and track user activity. And its primary function is to ensure secure, role-based access to IT systems. Now, we'll talk about role-based access in just a moment, but more generally speaking, this framework is the foundation of all security in any networking environment. Now, the first aspect is authentication, and this is always the verification of user identity, and I should also mention device identity, but it's always about verifying that identity before any kind of access is ever granted to any kind of system. Now, for most of us, the most common implementation of this.
All right, so in about 5 minutes, we'll be going to lunch, and I have the schedule coming up for this afternoon.
But those are not the only options.
Day 6 will start slides at 1400.
We also see biometrics.
When you get back from lunch, you can work on assignments from 1 to 2.
Scanners, smart cards.
Then we'll get into some quizzes or a lab like we did last week at 1600.
Or multi-factor
So that'll be the schedule for this session.
where any combination of methods is used to establish your identity. But that's the key. It's always the process of saying, this is who I am, and being able to prove that through the use of a password, a biometrics value, or whatever you might be using. Now, there are different protocols that can be used depending on what it is you're trying to access. So some examples include RADIUS, which stands for Remote Authentication Dial-In User Service. Now, the term dial-in quite literally goes back to the days when we used to use modems to connect to remote locations. But while we don't use dial-up services anymore, the authentication process is still the same. This is very common in enterprise networks when users are trying to access that environment from a remote location. If they're working from home or traveling, for example, they might connect to a VPN. So RADIUS can be used to authenticate those requests. Kerberos is very commonly used for user and device identification in what's known as directory services. The directory is simply the database of all user accounts and all devices, and when you log in, it basically verifies your identity and or your device. In a Microsoft environment, for example, the standard directory service is known as Active Directory, and it uses Kerberos as the authentication protocol. It handles the secure transmission of usernames and passwords, and basically is responsible for looking up your value in the directory, comparing it to the credentials that you just provided, and if everything matches, then you are logged in. Kerberos, however, is not just a Microsoft protocol. It is also used in Unix and Linux environments. And LDAP is the Lightweight Directory Access Protocol, which is still a directory-based authentication system, but it's more so used for specific applications. So coming back to the example of Microsoft's Active Directory, in that case, that's a proprietary implementation. But within that same environment, you might have a third-party application, such as a database or an accounting system, that also requires user IDs. Well, you can use LDAP to essentially pull the identities out of the Active Directory directory and import them into that application so that users can use the same username in the accounting application or whatever it is as what they use to log into the Microsoft environment itself, so that they don't have to maintain two separate usernames, one for each environment. Or you can still use it entirely on its own if, for example, you are only using any given application through something like a cloud environment. Then you might still just create the usernames and passwords for that application only, and it might use something like LDAP to handle its authentication. Authorization then is essentially allowing access. So it determines user permissions after authentication, and that's key. You can never be authorized unless you have already been authenticated, because authentication determines your identity. So once that has been set, then it's, well, what can you do? Or perhaps more to the point, what of those roles, and you determine appropriate or necessary to be able to do any particular task, then you place the appropriate people into those roles. Now, if the predefined roles aren't suitable to your needs, you can absolutely create your own rules. Then you can decide for yourself what the abilities are, but then you still place the people into the appropriate roles. That's all you have to do. As soon as they are added to the role, they have all of their abilities. Attribute-based access control is similar, but it's based on attributes of the security principle. In other words, characteristics of something like their user account. For example, perhaps they belong to a particular department. That's an attribute. So if I'm in the accounting department, I would have access to all of the accounting applications and whatever data and or files would be necessary. So then all you would have to do in this model is ensure that in the user's account, the department value is set to accounting in this case. That, again, will automatically give them access to the appropriate resources. Or you might see policy-based network access, which uses network access control policies for dynamic permissions. In other words, they can be set based on certain conditions which themselves might vary. For example, if I'm working from home and I use the corporate VPN to remotely access the network environment, then I might have more abilities as opposed to if I'm traveling and I'm connected to a public Wi-Fi. I might be much more restricted in that case. But the basic idea is that there are many different ways to access network environments, so it's based on the conditions. And then finally, accounting is, in this case, nothing to do with financial accounting. A better way to think of it might be accountability. So it's used to track user activity, login history, and resource usage. And this, of course, helps with compliance and auditing, as well as security monitoring. In terms of the compliance and auditing, you can demonstrate, you can show that this happened. So if you are being audited or reviewed, you've got the proof, so to speak. Can demonstrate what took place. Now, as for common accounting features, it includes log tracking, which maintains the user activity records, session auditing, which monitors active and past login sessions, and usage-based billing. Now, this is commonly used by service providers, such as in a cloud environment, to track network consumption. Now, in this case, this would actually be a little more related to financial accounting, because it literally is, you used this much of this service, therefore your bill is this much. So that's sort of a separate aspect, but it all falls under the umbrella of accounting, so to speak. So to finish up, as for some implementation best practices, you should certainly consider using multi-factor authentication, which enhances the security by requiring multiple identity verification steps as opposed to just something like a username and password. Regularly audit your access logs, particularly if you are a very regulated environment. So if you need to ensure compliance and detect any unauthorized access, regular reviews are critical, and implement what's known as the principle of least privilege when it comes to access control, which essentially means that if and or when someone does need access, that's fine, but restricted to only the minimum level necessary. Another way to put that is don't give your users access that is higher than necessary, and ensure redundancy in your authentication servers, which helps to prevent system failures. So in short, if one server fails, there is another one still available to handle your authentication. Okay, so again, there are different mechanisms by which all of these can be implemented, and it's certainly going to depend on the type of environment you're in and the platforms and types of devices you use. But one way or another, just about every environment implements some form of authentication, authorization, and accounting. In this video, we'll provide an overview of database servers, which are typically dedicated systems that store, process, and manage structured and unstructured data. Now, I'll come to the point about structured and unstructured data in just a moment, but database servers are also essentially the back end for applications, and they provide efficient data retrieval, storage, and transactions. And they're almost always used in business, cloud computing, and enterprise applications to maintain large-scale databases. So just quickly coming back to the point about supporting applications, most of the applications in use in most business environments require some kind of data, and that data is stored and provided by the database itself. In other words, the application doesn't really store anything. It accesses the data from the database. So there's always this interaction between the application that is installed on our end user devices and the data that resides on the database servers. So we need to be able to make these connections to the database servers to access that information. And if you've ever done something as simple as make a purchase online, then you've already used an example of this, because the web page or the app on your mobile device is simply a front end. It's just a means for us to access the information. So if I'm searching for a particular product, I'm entering a query, and it's the database server that provides the results and says, here are the products that you've just searched for. Now, in terms of the types of database servers, there are primarily two, and the first is known as a relational database server or a relational database management system, which stores data in structured tables with relationships. Now, the idea behind the table is that it always has the same type of structure. So just imagine a simple example of a table such as a spreadsheet, and if you just wanted to store simple contact information, then what you would see would be things like the contact name, and that might even be divided up into first name and last name so that you can sort by either one. Then you would probably have their email address, maybe their phone number, their physical mailing address, really anything that you want. But the idea is that you have these column headers such as first name, last name, email address, phone number, and then the information for any given contact is effectively the same. Now, I don't mean it's the same information, but it's the same type. In other words, if you look at the email address column, you will see nothing but a list of email addresses. If you look at the phone number column, you will see nothing but a list of phone numbers. So that's a structured table. Now, the relationships means that there can be multiple tables and there are connections between them. And sort of a classic example of this, if you will, is one table that stores customer information. So coming back to my online shopping example, if you log into that service and you have an account, then there is a table that stores all of your customer or your profile information. But then, of course, you make orders. But the orders that you make are not stored in the same table as your customer information. So the customer table stores just the customer information, but then when I make my orders, any given order is related back to me by specifying some kind of unique value, such as my customer ID. So let's just say that I'm customer number 1. Every single order that I make relates back to me because it says this order was generated by customer number 1. So there is always a relationship between the records in the customer table and the records in the orders table, and they're connected by the customer ID. So that's a relational database. But there are also non-relational databases, which are typically referred to as NoSQL. Now, SQL, or SQL, stands for Structured Query Language, and that's almost always the language that's used in relational databases, the structured query language. But if it's NoSQL, then this means that there really is no structure or some structure to the database. That's why we see unstructured and or semi-structured. But an example of unstructured data is just a document, really. If you think about any two documents, they are not going to have the same content nor any kind of tabular structure. You just write information into the document. A more common example might be if you're tracking things like social media posts. There's no structure to those posts. They could contain any information, but you might be tracking them to see what's trending. So that's basically unstructured versus structured. Now, semi-structured means that there can be some elements that are structured and some that aren't. As for the database server components, the primary component is known as the database engine, and this is responsible for processing queries and transactions. Now, a transaction is any unit of work that must effectively complete entirely or not at all. In other words, as long as everything did process correctly, then the record is written to the database. But if anything goes wrong, then the entire transaction is undone. It just goes away. For example, if you transfer money from one account to another in your online banking, if something fails, then that money can't just go away. It has to go back into the original account. So the transaction essentially never happened. Storage management is responsible for maintaining the data files themselves. So even though I talked about things like tables in a structured database, that data is ultimately stored in what's known as database files. So this is where you actually see the information written to disk. The query processor optimizes and executes database queries so that data can be retrieved as quickly and as efficiently as possible. And there is always a security and access control mechanism that implements things like authentication to verify the identities of the users trying to gain access to the data. And it implements things like role-based permissions so that some people would have access to just about everything, such as database administrators, while others would just be standard users, and they're able to access the data but not make changes to the database itself or implement any kind of security permissions. As for some database server deployment models, you can absolutely maintain your own database servers in your on-premises environment, and many organizations still do this. But like many other things, database services are also available in the cloud. So if you're already using cloud services, you can absolutely create your own database server in the cloud, or you can just create the database. Now, there still has to be a server somewhere, but if you choose to just create a database, the server is created and managed entirely behind the scenes, if you will, and it's up to the cloud provider to maintain the server itself. So we need only concern ourselves with the database. And you can also implement a hybrid database system where you have both. And you can even have the same database implemented in both environments. In other words, you can have a local instance of, let's say, database 1, then you can configure replication for that instance to the cloud. So it actually exists in both locations, and this improves your fault tolerance and the ability to continue to provide services should a failure occur in either location. Some database server performance optimization considerations include indexing, which is a process of speeding up data retrieval and optimizing queries by literally indexing the values in a table. And to give you a better idea as to what indexing is about, if you think of something like a textbook, there is usually an index at the back of the book or even a table of contents at the front. And either one of them will tell you that a particular topic is on this particular page. So that way, I don't have to read through the entire book to find what I'm looking for. I just check the table of contents or the index at the back and it says go to page 100. So that's exactly what happens in a database environment as well. Indexes are built on the tables, so if I query for a particular value, it tells me I can find that value in this location, and it can dramatically speed up query results. Caching is the process of keeping data and even the queries themselves in memory so that if I issue a query and my results come back, then someone else issues the same query or a very similar one, then the results are already there in cache, which always resides in memory as opposed to on disk, and the results come back much more quickly again. Load balancing is simply the process of distributing requests across multiple servers so that we can get better response times and also gain better availability, because again, if one server goes down, there are still other servers available to handle requests. And of course, just implementing regular maintenance such as backups, applying updates, and checking your index structure as well, because the data in tables does tend to change, and even the tables themselves will change. New tables will get created, old tables might get archived, so just staying on top of everything will help to ensure that your database continues to perform as well as it can. To finish up, the future of database servers includes implementing AI and machine learning, which can greatly enhance data analytics and automation. Blockchain databases provides a much more decentralized ledger of transactions that are maintained by a network of computers rather than a single centralized system. Each block also contains a cryptographic hash of the previous block, which creates this chain-like structure that creates a very secure and transparent record of the data that is extremely difficult to alter once it has been entered. Serverless databases are what I referenced a moment ago in terms of cloud-based databases. Now again, it does not mean that there is no server. There has to be a server somewhere, but it means that we don't need to manage them at all. So when you have a cloud subscription, you can literally go into the cloud and just say, I want to create a database. The server is then managed entirely behind the scenes. So this exists already, but this will continue to grow because it alleviates the management of the server, so we have less to concern ourselves with. And finally, edge computing and distributed databases can help to reduce latency, most commonly for IoT applications or anything that involves real-time communications. Now, most of these are all available already, but mostly in the cloud. So it depends, of course, on what you have in your environment. But one thing is for sure, databases of some kind of description will almost certainly always be around, because we will always need a means to store and access important information. In this video, we'll examine the Network Time Protocol, or NTP, which, as you might imagine by its name, is a protocol used to synchronize the clocks of computers and various other network devices. Now, it operates over UDP port 123, and it essentially ensures accurate timekeeping. So this is used in network security, logging, and really any kind of time-sensitive application. Now we'll take a closer look at some examples in just a moment. But with respect to how NTP works, for starters, there is a client request, which quite literally asks what time is it, for lack of a better word, so that it can synchronize its clock with the NTP source. Now, that source refers to what's known as stratum levels, and we'll take a look at those in just a moment as well. But the idea is that NTP is a hierarchical structure, so each stratum represents a level of that hierarchy. Again, we'll come to that in just a moment. But as per the request, the time is adjusted on the client to whatever it's told by the NTP source. From that point, it will continuously synchronize to ensure that it doesn't drift with respect to the source time. And again, this keeps all devices in sync with respect to everyone agreeing what the time is. So as mentioned, there are stratum levels in the implementation of the network time protocol, and this begins at stratum 0. Now, these are the actual clocks themselves. They're highly accurate time sources like atomic clocks or GPS clocks that are typically maintained by governmental agencies. But again, they represent the actual timekeeping devices themselves. From that point, stratum 1 refers to primary time servers running the network time protocol that in turn synchronize with the original stratum 0 sources. Now, there are several entities that maintain stratum 1 servers. For example, in the United States, the National Institute of Standards and Technology, or NIST, operates several stratum 1 network time servers, and there are other publicly available stratum 1 servers as well. And I'll give you an example of that in just a moment. Then stratum 2 gets its synchronization from any server at stratum 1. And this is where you typically find systems that will provide synchronization to client systems. In other words, we can probably implement our own servers at stratum 2. So in my organization, if I want to implement NTP, then I make a connection to a stratum 1 server. In other words, I would not have access to stratum 0, the actual devices themselves. Access to those would be highly regulated. So stratum 2 represents the level at which any of us can implement our NTP servers. Now, there is stratum 3, and this would be optional, for lack of a better word. It would represent better word, it would represent further downstream devices that are still synchronizing with higher stratum servers. Now, you can continue this, but the farther away you go from the original source servers, then the less accurate it's going to be. Now, that said, things like the stratum 1 servers that directly communicate with the stratum 0 devices would likely have dedicated connections that don't carry any other network traffic, and they would be very fast. But it still takes a certain amount of time for the information to get from the source to the next stratum. So there would always be a little bit of an offset. Now, the protocol deals with that because when any time is issued at any stratum level, it also includes a timestamp as to when it issued the time. So when the system receives it, it can compensate for that latency. But as you go farther and farther upstream, it just has to continually compensate. So again, the farther you go, the less accurate it's going to be. But the protocol itself does support stratum levels up to 15. So it depends on what you need, obviously, but any given stratum level can only synchronize its time with devices in the stratum level directly ahead of it. So 3 can only synchronize with 2. 2 can only synchronize with 1. Okay, so again, it's up to you how far down you want or need to go, but try to keep the stratum levels at a minimum. As for configuring NTP, you do have to initially choose your source NTP server. And this is what I was talking about in terms of choosing a publicly available server. And there are a few different options depending on where you are. But one example is pool.ntp.org. You can simply go to that site and you choose your source server. Now that said, you don't necessarily have to use a publicly available server. You can implement your own system within your own environment and basically use that as your source. But that system would not be synchronized with any publicly available NTP server, but that might not always be necessary. If you only need to synchronize operations within your own organization, then it doesn't matter if you're synchronized with the rest of the world, so to speak. So it comes down to what your needs are, but you have either option. You can choose a publicly available NTP server or your own. From that point, you edit the NTP configuration file, which just specifies things like how often it will synchronize and various other communication parameters. Then you enable NTP services on that system. You just make sure that the service is started so that it can respond to other systems, and then verify that synchronization is actually occurring from those other systems. And you can use various command line tools to determine that, but it depends on the type of device that you're using. So then, why do we even need such accurate timekeeping? Well, for applications that are in any way related to security and compliance, timestamps are critical for things like event logs, audits, and investigations. You need to know that this event occurred at that time so that you know that you're dealing with the correct events. Network coordination ensures consistency in distributed systems and many different cloud services. Any kind of distributed system needs to know what time anything took place because many tasks are related sequentially or they have to occur at more or less the same time. Financial and industrial applications require accurate time as well for things like stock trading, banking, and automated processes. And telecommunications such as cellular networks and voice over IP also require very accurate time synchronization. So it is a component of networking that's a lot more important than people might realize. Finally, some future trends in time synchronization will likely involve expanded use of the precision time protocol. Now, this is exactly the same type of protocol in terms of what it does, but it's far more accurate in terms of precision, as is indicated by its name. So for very mission-critical applications that require very precise time synchronization, PTP is a better option. Cloud-based time services will also likely continue to expand. Providers like Amazon, Google, and Azure do offer very scalable time synchronization for all of our cloud-based applications and services. Quantum timekeeping is evolving and developing, and this uses quantum clocks for unprecedented accuracy. And 5G and IoT integration can support very precise timekeeping for next-generation networks, such as those that we're starting to see emerge in things like smart cities and just the various types of applications that are being implemented in 5G environments because of the bandwidth support that 5G offers. They enable the implementation of ultra-low latency applications. So again, these are types of networks that typically include a multitude of different types of devices, many different applications, and many different communication protocols, but they can all integrate to support things like smart cities and just very complex networks. Ultimately, time synchronization is a necessary service, so NTP and PTP are definitely protocols that you should consider implementing if you need accurate timekeeping services in your environment. In this video, we'll take a look at internet appliances, which are specialized network devices that provide dedicated internet-related services. Now, we'll see some examples of what those services are in just a moment, but internet appliances can be used in just about any environment, including home, business, and enterprise environments for security and connectivity, although they're less likely to be found in a home environment, almost certainly in an enterprise environment. And they are hardware-based. As soon as you see the term appliance, then this does mean that it is a hardware unit. But these days, particularly if you're using cloud-based services, you can simply subscribe to their services. In other words, if I don't have the means to implement something like a firewall, then the cloud provider I'm using would absolutely have them, and I can just configure them accordingly to protect my resources. So I can access the configuration and set them up however I need to, but I don't need to look after the actual hardware itself. That's up to the provider. So as for some common types of internet appliances, they include the aforementioned firewalls, VPN gateways, content filtering devices and or proxies, load balancers, and IoT or Internet of Things gateways. Now, as far as a firewall appliance is concerned, when it's implemented as an appliance, this is typically a rack-mounted device that would look similar to a router, for example. But this type of firewall would almost always be implemented to protect the network, as opposed to a host-based firewall, which is often just software on any given system that would protect that system itself, but really nothing else. A firewall appliance is typically placed right at the edge of the network. It sits between you and the internet, and it protects your entire environment from threats on the internet. A VPN gateway is also often referred to as a VPN concentrator, and they're used if you have a lot of remote users that all need to establish connections into the network from wherever they are, be that working from home or while they're traveling, but they all gain access through this single device. That allows you very centralized control and management of all of your connections, and you can configure various policies that determine how and when and who can connect, and they can all be implemented at the gateway itself. Content filtering devices and or proxies can be used so that when users just go out onto the standard internet, you can ensure that only appropriate content is allowed to be viewed or accessed. In other words, everyone goes through the content filtering device. Your connection is actually terminated at the content filtering device or the proxy, then it goes and gets the content for you. But an administrator can block certain sites that are questionable, or those that are just often used for personal activities such as video streaming. You can block those in the work environment to prevent people from wasting time and using up bandwidth. So it allows you to simply control what type of content is accessed. Load balancers do exactly that. For incoming requests, such as for a website, you might have thousands upon thousands, even millions of incoming requests. So you can place multiple copies of your website across multiple servers. Then the load balancer equally distributes requests across all servers. So if, for easy math, you have 4 servers, then each one would receive approximately 25% of the requests. The load balancer is responsible for ensuring that it is balanced equally, and it even provides fault tolerance, because if one of the servers were to go down, that's no big deal. The other 3 are still there, so the load balancer will just dynamically adjust so that each surviving host receives approximately 33% of the requests as opposed to 25 until the other server comes back online. And IoT gateways are similar to VPN gateways, except VPNs are for users to gain remote access to the network, whereas IoT gateways gives you still that centralized connection point, but for IoT devices. So every device communicates through this centralized gateway, and that allows you to better control and manage the traffic for whatever applications they're supporting. As for the functions and benefits of internet appliances, well, of course it depends on what the type is, but they certainly can offer enhanced security to protect against threats and data breaches if you're talking about something like a firewall or even a content filter or a proxy, because that can prevent our users from gaining access to questionable websites. They can certainly improve network performance by optimizing traffic flow, particularly through load balancing, and they offer simplified management because they're all centralized. So this reduces complexity and gives you better control by just implementing your configurations on each type of device. And they can also help you to meet any regulatory requirements with respect to monitoring and or logging or performing analytics. So again, it does come down to the type of device with respect to whether or not it's required in your environment, but they certainly can help you to ensure that you are remaining compliant with various types of regulations. As for deploying internet appliances, you do have to make sure that the devices you're implementing can handle the load. So in terms of scalability, you'll want to be able to ensure that they can be upgraded or that you can simply implement more of them. And in terms of security policies, you'll need to configure your firewalls based on your particular organizational needs. There's really no right or wrong configuration for a firewall because different environments need to allow or block different types of traffic. You'll also need to ensure that they can integrate with your existing infrastructure, so verify compatibility with things like your routers, switches, and any cloud services that you might be using. And since they are physical appliances, you do need to make sure that they are maintained, so apply regular firmware updates to address vulnerabilities, and just generally monitor their health and make sure that they are able to keep up with the workload. Finally, some emerging technologies in internet appliances include the integration of artificial intelligence with respect to security appliances, which can better detect and respond to threats in real time. Edge computing integration refers to enabling faster application processing by moving your workloads closer to where they're being consumed. So, as an example, something like an IoT gateway. If I have a new workload in a completely new location, then I can implement an IoT gateway closer to that location to help reduce latency and improve performance. 5G and IoT expansion will help to support more secure connectivity for next generation wireless networks. And this is another example where something like an IoT gateway would come into play. And finally, the aforementioned cloud-managed appliances are simply becoming more and more common. So there is still a physical appliance at the cloud provider, but all I do is subscribe to the services of that appliance, meaning that I do not have to look after the physical appliance at all. So I certainly pay for the services, but it's on a monthly basis, and there are no hardware concerns whatsoever. It's up to the provider to ensure that the device is maintained, so I only need to concern myself with the services. So this is becoming more and more common as more environments start to move toward the cloud. So whether you implement actual physical appliances or their cloud-based counterparts, it simply comes down to the services that you feel are required for your organization. But in many cases, internet appliances can provide those services for you. In this video, we'll provide an overview of legacy embedded systems, which quite literally refers to older computing systems that remain in use despite advancements in technology. And they're referred to as embedded, typically because they're often tightly integrated with industries such as manufacturing, healthcare, transportation, government infrastructure, and many others. And they're often designed for a particular task, which can make replacement costly and complex because, again, they are specifically designed for that purpose. So it's not like just going out and buying new desktop computers or new mobile devices. Everything would have to be entirely replaced in many situations. So again, you will often find legacy embedded systems still in use. But of course, this introduces a few challenges, perhaps most notably security vulnerabilities. Because they are old, they generally aren't updated anymore, so there could be vulnerabilities in many aspects of the system. And because both the hardware and the software is typically quite old, it will likely be incompatible with newer hardware and software. And this, of course, introduces higher maintenance costs because it can require specialized skills and specialized hardware and software to keep up with maintenance. And it may often have limited scalability because they are typically designed for a very fixed purpose. So there's generally very little room for expansion. So in terms of a particular or more specific example, there is a classification of systems known as SCADA, which stands for Supervisory Control and Data Acquisition, which is generally a control system used for monitoring and managing industrial processes. Now, some common examples of these might be power plants, water treatment facilities, and manufacturing, and it typically operates using a combination of sensors, remote terminal units or RTUs, and human machine interfaces or HMIs. Now, the reason why SCADA systems are being singled out is quite simply because many SCADA implementations rely on legacy embedded systems for their data collection and automation processes. So transitioning a SCADA system to a more modern architecture can be quite slow due to the cost and the operational risks of performing the upgrade, because in many cases you might have to entirely remove whatever is currently in place and then replace it with something that is entirely new. So that in itself can cause significant delays when it comes to upgrades. So in terms of some strategies then for managing legacy embedded systems, you can try to segment the legacy networks. In other words, isolate those legacy systems from your newer applications and services to minimize security risks. If possible, implement virtual machines to run any legacy applications on more modern hardware. You can likely do this in many cases, but it will depend on the application. But if so, you can take advantage of modern hardware to run that application more effectively, and certainly apply any security patches when possible. It's not as though legacy systems don't have any updates, so keep an eye out for what might be available and try to plan for some kind of a phased upgrade. Now, again, that might involve entirely removing what you have and completely replacing it with something else, but in some cases that might be necessary. So to finish up, as to the future of legacy embedded systems, you might be able to take advantage of edge computing, which helps to bring the processing power closer to legacy systems to improve real-time data analysis. These systems still often generate data, so we can take advantage of processes such as edge computing and cloud integration to simply take advantage of the processing capabilities of both of these services, which can of course generate better data more reliably, faster, and likely at a lower cost as well. You might also be able to leverage AI-driven automation, again with respect to the data that is being generated. AI and machine learning can still be used for processes such as predictive analytics. And in terms of any upgrade that might happen, you should certainly be mindful of any regulatory compliance improvements. In other words, governments and industries might be pushing for more modern security standards within your legacy infrastructure. So at some point you might be required to upgrade. So again, this is something to consider, but that will certainly depend on the infrastructure that you do have in place and of course the industry that you're in. But when it comes to legacy embedded systems, it's not as though you always must upgrade simply because it's a little bit out of date. It may have been specifically designed for a particular purpose, yes, but it may perform that purpose very well. So again, it's going to depend on the situation, but sooner or later, it's likely that you will have to upgrade. So just bear these considerations in mind when it comes to what you have versus what you have available in terms of upgrades. In this presentation, we'll provide an overview of IoT, or the Internet of Things, which refers to quite a variety of interconnected devices that can all collect and exchange data over the Internet. Now, that's a fairly generalized description, but there are many different types of implementations. For example, IoT can be used in smart homes, industrial automation, healthcare, agriculture, and many other industries. But some more specific examples of the devices themselves include smart thermostats, wearable health monitors, autonomous vehicles, and really any type of device that can gather data and exchange that with other devices and or submit it to an application for processing. As for how the devices themselves work, it includes a network of sensors and monitors, which again are responsible for gathering up data. And this can really include just about anything that can be measured: temperature, pressure, motion, humidity. In the aforementioned health monitors, things like your heart rate and or blood pressure. So again, the idea is to simply gather up all of this data. Then there are typically edge computing devices which will receive the data from all devices, and once everything has been gathered, it will typically upload that data into the cloud, where it can be stored more effectively and, perhaps more importantly, analyzed. And then we can see some kind of a user interface which can display insights from that analysis through mobile apps or various types of dashboards. This, of course, presents us with the useful information that can be generated from that raw data. So there are some network considerations, however, for IoT devices with respect to how they communicate with each other. And some common examples include Wi-Fi. For example, in smart homes or offices, we can have any number of IoT devices which again can gather up information and then present us with more meaningful insights. So a common example in the home might be your environmental controls, your heating and air conditioning and air circulation. It can measure all of the conditions, and apart from simply turning on the heat and or the AC when we need it, it can provide us with data so we know how much we're spending, and we can see if there are any areas for improvement in terms of efficiency. Bluetooth and Zigbee can be used for short-range communication for many smart home devices. Now, again, this would depend on the system, but things like home security systems might also be part of your smart home. Cellular, including 4G and 5G, can provide reliable connectivity for remote applications and devices. For example, fleet tracking or your field worker devices where they would not have access to things like Wi-Fi and the distances would be too far for things like Bluetooth. And you can also implement LPWAN, which might include LoRa and or NB-IoT. Now, LPWAN is low power WAN, LoRa is long range, and NB-IoT is narrow band Internet of Things. But these are all used for various types of low power, long range IoT devices. So again, it's going to come down to the types of devices being used in terms of how they'll communicate with each other. But there are some security challenges when it comes to IoT. For example, there can be weak authentication in that many IoT devices might use default or hard-coded credentials, and in fact, some may not have any authentication mechanism at all. There can be data privacy issues in that the personal data collected by IoT could be misused if it falls into the wrong hands, so to speak. DDoS attacks, or distributed denial of service, is common with IoT devices because they can be used in botnet attacks, and any unpatched firmware might result in vulnerabilities because the devices might simply lack regular security updates. Again, it will depend on the type of device and its purpose with respect to what kind of authentication and or security might be available. As for some of the best practices to help improve that security, though, certainly implement strong encryption using TLS or transport layer security and VPNs for data transmission. So even if the devices themselves don't support particularly strong security, you you can certainly still implement secure data transmissions when you're sending that data to the cloud, for example, to be processed. You might also be able to implement multi-factor authentication for device access. Again, this will depend on the device, but if it supports it, then that's certainly more secure. And just be mindful that there still can be updates, so it's always a good idea to simply check to see if any are available, because most of the time, if a vulnerability is discovered, the vendor will release an update to correct that issue. As for some applications of IoT in the various sectors, common examples include healthcare, whereby you might see remote patient monitoring and smart medical devices being used to transmit the condition of the patients. Smart cities might implement more intelligent traffic lights, more efficient waste management and security cameras for better monitoring. Agriculture might implement IoT-based weather monitoring, irrigation control, and tracking their livestock. And in manufacturing, you might see predictive maintenance and or automated production lines, all to help improve the overall efficiency of the processes. And finally, as for the future of IoT, I would certainly expect artificial intelligence and machine learning integration to only enhance IoT decision-making capabilities through better data processing and analytics. With 5G expansion, we can expect faster, lower latency communication for IoT devices, making real-time communications more accessible. Blockchain for security can help to decentralize authentication for connected devices, and edge AI computing can run AI models locally on the IoT devices themselves, again for real-time decision-making. Now, again, this will all come down to the particular application and or the devices being used, but it's certainly something that is only going to become more and more common as our existing devices get smarter, for lack of a better word, and new devices come online. So IoT is certainly an aspect of information technology in general that is only going to continue to grow. So in this course, we've examined networking concepts and configurations. We did this by exploring IP addressing, including IP version 4, IP version 6, subnetting, and automatic private IP address configurations, DNS and DHCP services, configuring network name resolution and dynamic addressing, server roles, including file servers, web servers, authentication servers, and database servers, the network time protocol and internet appliances and ensuring synchronized and secure operations, and legacy embedded systems and Internet of Things devices and managing network devices in modern IT environments. In our next course, we'll move on to explore internet connection types and features.